Cochlear implant users often struggle with tasks that require proficient frequency discrimination abilities, including listening to music, understanding speech and noise, interpreting intonation, and identifying speaker gender. The ability to detect frequency changes is highly correlated with speech outcomes in CI users. This project serves to examine how the brain processes frequency changes in new cochlear implant recipients by using event-related potentials, psychophysical methods, and speech perception scores. The Acoustic Change Complex, or ACC, is an event-related potential elicited by change embedded in the middle of a stimulus. Waveform morphology includes a negative peak, approximately 100 milliseconds, followed by a positive peak, approximately 200 milliseconds, after the change in the stimulus. The ACC can be reliably used as an objective measurement of frequency and intensity discrimination. Our study includes 8 CI recipients activated within 3 months of testing. 2 participants were repeatedly tested several weeks after initial testing. Speech perception measures include the CNC word list, AZ Bio and Quiet, AZ Bio Sentences and Noise, and the triplet digit test. Psychophysical measurements include the frequency change detection threshold, a 3-alternative forced choice procedure to determine the minimal amount of frequency change required that can be detected by an individual. The frequency change detection threshold stimulus used were a 1-second pure tone with an upward frequency shift located at 500 milliseconds. 3 base frequencies were used, including 250 Hz, 1000 Hz, and 4000 Hz. The electrophysiological responses used in the acoustic change complex measures the N1, or a negative peak, and the P2, the positive peak, occurring after the frequency onset and frequency change of the stimulus. Stimuli used mirrors the frequency change detection threshold stimuli, with an upwards frequency shift embedded in the middle of a 1-second pure tone. 3 base frequencies were used, 250 Hz, 1000 Hz, and 4000 Hz, each with an upwards frequency shift of 0% change, 10% change, and 70% change. Waveform responses were analyzed using independent component analysis to remove stimulus artifacts. Data gathered from short-term cochlear implant users yielded worse responses compared to long-term cochlear implant users. This previously collected data from our lab. Our relationship between behavioral responses and ERP waveforms was not observed in new CI users. The users with the largest ACC waveform, such as participant 2, were not the same individuals with the best behavioral performance, such as participant 4. Similarly, the individuals with the best behavioral performance were not the participants with the best ACC. It is possible that changes in ERPs and the change in behavioral responses do not occur with the same pace, or the former may precede the latter. More data is needed to examine different time points after CI activation in order to observe natural plasticity.